So far, you've learned that a cluster is made up of a large number of conventional machines, and so it has a high degree of concurrency, but it also has a high probability of experiencing a wide variety of failures. In this lecture, we're going to learn about distributed batch systems. And a distributed batch system is the first element of software used to manage a cluster so as to harness the concurrency while dealing with the failures that are likely to occur. First, you have to think a little bit about what a big cluster is actually like. A big cluster isn't something that you keep in your office, isn't something you keep in the basement. It's typically something that's in a data center that's located close to power utilities and networking, and it's often in an inconvenient place. It could be out in the country, it could be in a converted train station. It's going to be somewhere that's probably far away from the users that want to use it. And inside that data center, we're going to have rows and rows of racks that have power and cooling in an environment that's actually pretty unfriendly for humans. You can walk through it and take a tour, but you wouldn't want to sit and work in 55-degree temperatures with all of these machines whirring. So we have a lot of people want to use this cluster, but the reality is they don't walk into it in order to use it. They have to use it from a distance. So when you use a cluster, you're probably going to be sitting in your office at your desktop machine, but you're going to be using some remote software in order to connect to that cluster and instruct it what you want it to do. You could imagine using SSH or a terminal program in order to connect in and do whatever you like to a cluster. And I suppose that's possible, but we'd call that situation an uncontrolled cluster if we simply allowed everybody to log in and do whatever they want. But it's useful to think about what an uncontrolled cluster would be like, because it's going to explain why we need a distributed batch system. So suppose that we have an uncontrolled cluster such that anybody could just log in and use whatever machines they wanted in the cluster whenever they wanted to. Right, so here's our picture of a cluster again. And now suppose user A comes in and wants to use half of the cluster. And just by convention, user A picks the machines from beginning to end and takes half of those machines, starts using them, and for the moment A is happy simply because nobody else is using the cluster. Well, now user B comes along, and user B has no way of knowing which part of the cluster that user A is actually using. So maybe user B also wants about half of the cluster, but picks a different slice of it. So down here, user B is getting some nodes all to herself, but up here, user A and user B in conflict because they're both trying to use the same machine simultaneously. Each one of these machines is running a local operating system, and if you know something about local operating systems, well, that's allowed. You can run two programs simultaneously, but when that happens, they're going to be sharing the CPU, they're going to be sharing the memory, they're going to be sharing the disk, and as a result, on those nodes, they're probably going to be running half the speed that they ought to be running simply because they're sharing the same resources. If they're really unlucky, they might overload the system and consume all the memory or all the disk, and then on those nodes their programs would crash. So they might be upset. But suppose for now they continue on that way for a while, and then another user comes in and picks a different subset of machines to use. Well, now user C here has a couple machines to themselves, but they're in conflict with user A over here, they're in conflict with user B over here, and then we have a couple machines that are really overloaded. In fact, we call this a load imbalance, because we have a bunch of machines that are really under high stress and a bunch of machines that are unused, and so we're seeing contention even though the cluster isn't fully utilized. Now imagine even more users come in. Well, they line up and things just get worse from there. An uncontrolled cluster isn't really what we want to do. If we have an uncontrolled cluster, then the users have to guess where they're going to log in and what machines they're going to use, so it's pretty inconvenient for those users, and they're not likely to make good choices. If you have multiple users, they're going to get in conflict, and that's going to result in slowdowns and crashes, so that's not good for the users. The cluster is not likely to be fully utilized, so that's a waste. A big cluster like this costs a lot of money, and it would be a shame not to have machines in use when there's somebody who wants to use them. And there's no way to enforce any notion of fairness or priority according to whatever local policy you want. Maybe you want everybody to have an equal amount of service. You're not going to get that in an uncontrolled cluster. Or maybe you want some users to be more important than others. You're not going to get that either. So an uncontrolled cluster is not a good situation, and what we need to do is instead use a distributed batch system. You can think of a distributed batch system as the software that manages the whole cluster and makes scheduling decisions. It's sort of like an operating system for a cluster, because it's going to manage lots of programs and make sure that every program gets the right resources and is treated fairly. Now, when using a distributed batch system, The user can't just come in and start using machines willy-nilly. Instead, they have to describe what it is that they want to do in the form of a job and submit that job to the distributed batch system. The batch system then sets priorities among jobs, dispatches the jobs to the nodes, and makes sure that they execute. The most important thing that a batch system does is that it ensures that no jobs are going to overlap on the cluster. So independent of everything else, if we can simply assure that every user gets different nodes, then things are going to go well. On top of that, the batch system might enforce scheduling policies to make things fair or to enforce priorities, depending on what the owner of the cluster wants to do. So now, let's think of the same example, but this time with a distributed batch system in place. We have our cluster, we have the distributed batch system which is going to manage it, and that batch system has a queue of jobs that it is going to run. And now when users come to the system, they define what sort of jobs that they want to run. So let's suppose a bunch of users come to the system all at once and describe what they want to run. User A wants to run one job that needs 18 nodes. User B wants to run one job that needs 15 nodes. User C, 12 nodes. And user D wants to run 3 jobs, but each of those jobs only needs 1 node. Now let's suppose that the distributed batch system is now going to schedule these in order if it can. So it looks at user A first and says, okay, I have 18 nodes available. I'll schedule you to those nodes. So users A job starts running. It looks at users B and says, okay, I have 15 nodes available. Let me place you on that part of the cluster. And now user B is happy. And because A and B are isolated, they should both get the full performance of the system. To be fair, to follow the list, we might say user C should run next. But the problem is that user C wants to use 12 nodes, and we don't have 12 nodes available. So we have a choice here. If we want to strictly follow a first come, first served scheduling policy, then we should wait until something finishes before scheduling user C. But we can see that we've got 3 nodes available. We could go ahead and schedule user D, and if our goal is to maximize the utilization of the cluster, then that's what we ought to do. This is also known as backfilling, because what we do once the cluster is scheduled as many jobs as it can in first come, first serve order, we go back and try and fill in the gaps. So let's suppose we fill in the gap with user D. Eventually, user A's job is going to run to completion and exit, and so it will be removed from the system, leaving half of the cluster available. Now we do have space to run user C, so the batch system will schedule user C into that available space, and everybody moves up into the queue. Now this will go on and on and on as more users come into the system, and the system will decide to schedule it if they can, and otherwise to let them wait in the queue. So here are the advantages to having a batch system. The first is that the users no longer have to worry about the details of which machines they're going to use and where they're going to log in, which is a big relief. All they do is submit their jobs and let the batch system schedule where it's going to be. By running on different nodes of the system, the jobs will not interfere with each other, and so each job will get the maximum performance that is available. That batch system also provides a central point of control. Now that cluster has an owner or some operators that need to make some decisions about who runs first and when things run and how to schedule things, and so the batch system becomes the place where they can enact those policies. But here's the trade-off. If you use a batch system, our users have to get used to the idea that they're not really in control. So they're going to submit their jobs, give up those scheduling decisions to the system. They're going to gain some benefits from that. But they have to have some flexibility because they can't decide exactly when and where they're going to run. So that's the purpose and the advantages of using a distributed batch system.